So this is the New Technologies in Mathematics seminar series of the CMSA at Harvard University, and I'm Mike Douglas. And this week we're delighted to have Patrick Messaud from Orsay and from the CNRS to tell us why we should explain mathematics to computers. And I'll remind you that question, while you can freely ask questions, I offer to look at questions that you post on a chat, and then to raise the question at an appropriate moment in the talk, or even to answer it myself if it's something simple. And we'll of course have a few minutes for questions at the end of the talk. So with that, Patrick, go ahead.
Thanks. Thank you very much, Mike, for the invitation. And I hope there are people here who actually don't already know the answer to this question that is my title. I also hope that you can see my slides. Can you currently see my slides, or is it broken again?
I see them.
You see your message. Okay. So our goal with this whole area of explaining mathematics to computer is to extend the mathematical toolbox. And I want to insist from the very first sentence that we want to keep everything we like in mathematics. We want to keep the old way of doing mathematics, but we want to add something more. And why we need to add something more, this is the topic of the talk, but I'm not proposing that we stop doing mathematics the way we do it usually. So the goal of today is to see what it looks like to explain mathematics to a computer. The main point will be to explain why we want this. And in my talk, I will try to be careful distinguishing what already exists, what we hope will exist soon, and what is total science fiction. Because with all, I guess, those technology talks in this seminar, maybe sometimes it's not easy to understand what already works and what is the future. So if this is unclear, please ask questions. And all the examples that I will show you will be used Lean, which is a software developed mostly by Leonardo de Moura at Microsoft Research, but there are other options if you want to explain mathematics to a computer, especially a software called Coq and Isabelle. But I won't show those software to you because I don't know how to use them, basically. But keep in mind that other options exist. So I want to do very soon a demo because otherwise you don't understand what I'm talking about. But I still need some mathematics to explain to my computer. So I've chosen to explain the Heine-Cantor theorem to my computer because this is an elementary theorem that I hope you all have already encountered. And the first thing is I need a proof. I need to understand the theorem. I'm not going to ask my computer to prove this theorem without any input from me. So I need to first explain one proof that fits on one slide. So I will have to cheat a bit and use something to reduce the size of the proof. I want to prove that any continuous map from a compact metric space to another metric space is uniformly continuous. And I will do it using the extreme value theorem to handle all the heavy lifting. So here is the proof I want to explain. So first, the goal is to prove that for all positive epsilon, there is a positive delta, so that whenever x and y are at distance less than delta, their images, f of x and f of y, are at distance less than epsilon. This is my goal. And oops, so the proof starts by fixing some positive epsilon, any1. And I introduce this set K, the set of points in x times x, whose images are at distance at least epsilon. Those are the bad points in a way. So K, this set K is closed because the function f is continuous by assumption, and the distance function on x times x is also continuous. Since x is compact, x times x is compact too, and so K is a compact subset. And now this is where I use the extreme value theorem. It gives me P in K, which achieves the minimum of the distance function, which is continuous, on K. So for all Q in K, distance between P1 and P2, so remember K is inside x times x. So P1 and P2 are the 2 points corresponding to P. So distance between P1 and P2 is less than distance between Q1 and Q2. And now I say that the delta I'm looking for is the distance between P1 and P2. That will do. So I fix x and x prime in x, and my goal is to prove that, oh, there is a typo, sorry. Whenever distance between x and x prime is less than distance between P1 and P2, which is my delta, the distance between f of x and f of x prime is less than epsilon. And if I contrapose this implication, the goal is to see that if, so now there is no longer the typo with y, so whenever x and x prime are in K, the distance between P1 and P2 is less than the distance between x and x prime. And this is exactly the defining property of P, the property that was given by the extreme value theorem. So this is a small proof that I want to explain to my computer today for you. Okay? So I need to somehow copy-paste this and explain this to my computer. So I need to switch to some different software. Okay, does it work? Do you see something different? So I will just paste what I had previously, and you see what I had as was the statement. So I've got a metric space X and a metric space Y, and X is compact. F is a function from X to Y, and I have the assumption HF that F is continuous. And my goal is to prove that F is uniformly continuous. And the first thing to notice is that my computer doesn't like this proof. There is red all over my screen because the computer is not yet able to understand this natural language explanation. So I need to just comment all this, and this will guide me, but this is not what my computer will understand. And there are people working very hard to make sure that one day the computer understands directly what we type and say the text source of our math paper, but this is clearly science fiction at this point.
Patrick, maybe make the font a little bit bigger.
Is it better?
Perfect. Yeah, that's good.
This is too much, or maybe this is not too much. Let's try this. And now, you see the window is divided into two parts. On the left is where I'm writing, and on the right are the answers from the computer, and the so-called tactic state. It shows everything that I have around. So I see that X and Y, I don't care too much about this part, but X and Y are my metric spaces, and I've got this compactness assumption, a function F from X to Y, my continuity assumption, and after the funny symbol that looks like a T that has fallen on the side is my current goal. And there is one goal, which is to prove that F is uniformly continuous. So the goal is spelled uniform continuous F. So now I want to turn it into this for all epsilon. So I will rewrite using some lemma, which is uniform continuous if and only if. And in this case, I use the fact that I know the name of this lemma, and we will discuss more later how I could have avoided that. So now the goal has changed. The goal is no longer that F is uniform continuous. Is as expected the fact that for all for all epsilon real number, if epsilon is positive, then there exists delta, which is positive. And so that for all AB, distance between AB less than delta implies distance between F and A, F of A and F of B is less than epsilon. I don't know why the display is a bit funny. I don't know why. Okay, let's ignore that and still write bigger. So this fixed epsilon positive is spelled intro epsilon and epsilon post, and you see I write some small commands on the left, and after writing this introduction command I see that epsilon has been fixed. Epsilon is a real number, and I have an assumption that I named epsilon post that tells me that epsilon is positive. And now I need to find this delta, which is positive, and so on. So the next line was this introducing k. So this I could almost copy, except that I don't want this capital S. And this is P1, distance between f of P1 and f of P2. This is my k. What is it?
You need to remove the
So this is
around delta, around the distance function.
I should have. I tried to almost not modify the thing, but it's not quite. Okay, so this is what I want. So this is my capital K, and now I claim that K is closed. So I will claim that K is closed. I have that K is closed, and the explanation was that K was closed because f and distance are continuous. So now you see I've got two goals. The first goal is to prove that K is closed because I just announced that. And the second goal is what I had before. So let's focus on this first goal and ask for suggestion from the computer. So maybe I ask the computer to suggest me something to prove that K is closed. And first, it suggests me things like proving that the complement of K is open, or maybe use that K is finite, which is clearly not true, so that won't work. But there should be something more promising. So this speaks about LE, which means less or equal. So let's do that. And now I need to prove that the function sending any P to epsilon is continuous. So probably the computer has ideas for me. Yeah. The computer says, try this exact continuous const. So let's do that. And what else was it to do? I'm lazy. I will again ask for suggestion to prove that this function is continuous. And probably, I'm going fast through the list of suggestions, and I see something talking about continuity of distance. And I keep going like this, asking for suggestions for next step. Yeah, that looks good. And the same will work probably for the rest of the proof of this. Suggest something to me. And that's done. Now my goal has been accomplished, the goal that I was focusing on. So this is a bit ugly to look at, so I will just try to ask the computer to tell me how to compress this. And now I've got a proof that fits on one line, and I can move on. I move on, now my set K is closed. And this was the comment that was going with this proof. And now I have that K is compact. And again, this should be something easy. Yeah. So this is easy because it's closed set in a compact. So the computer was able to understand that K is compact. And then, so this is this line that I just formalized. And now I have the extreme value theorem to apply. So let's state this. I want to obtain P in K so that for all Q in X times X, if Q is in K, then the distance between P1 and P2 is less than the distance between Q1 and Q2. So let's get suggestions about proving that. So my computer is thinking, and it thinks maybe using K compact is a good idea. So it suggests K compact dot exist for all LE. That's very promising. So let's do that. And now something happens. Now I've got 3 goals. The second goal is continuity of the distance function on K. That was expected. And this is the remaining of my proof. But the first goal is to prove that K is non-empty. And I didn't have a line for that in my Beamer proof. So what happened? Maybe this is because it's a remote talk, so nobody.
You got a false proof, Bastards.
Okay. So this is not correct. And funny fact, if you go to Wikipedia and look up the extreme value theorem, I did that yesterday, and the non-emptiness condition is missing from this version of the extreme value theorem on Wikipedia. So probably before the end of this talk, someone will have fixed Wikipedia. But right now, this non-emptiness condition is missing. And there is no reason why K should be non-empty, because there could be no point at all that are sent at distance more than epsilon by f. For instance, f could be a constant function. And of course, this constant function is uniformly continuous, but this set K would be empty for a constant function. So I really need to change my strategy a bit. So I will do a proof by cases. Maybe K is empty or it is non-empty. And what is it? Ek empty or non-empty? There is no underscore here. Okay. So now I've got two cases to consider. In my first branch, K is the empty set. And in the second goal, I assume that K is non-empty, and I have to prove stuff. So let me go quickly. I just cheat and paste the proof in the case where K is empty. In the case where K is empty, you could use delta equal 1 and just finish the proof very easily. And now assume that K is indeed non-empty. And now I can use that non-emptiness condition and use some suggestion about proving continuity of the distance function. Suggest me some proof. Suggest, yeah. So I can compress this a bit. Because now I want to look smart. So you forget that the computer did all the steps for me. Okay, and now I've got my minimal value P. And I can use, as I promised, the distance between P1 and P2 as my delta. And now the goal, this funny symbol is a logical AND. So I've got actually two things to prove. I need to prove that this delta is positive, and then I need to prove it does the work. So what was my proof of the fact that delta was positive earlier? And my proof was, let's use this delta and pretend it's positive. Now, if you think about this proof that I had before, I was not using that epsilon is positive anywhere. Because this is how we teach students to find gaps in proofs. I mean, if the proof starts by, let's fix a positive epsilon, and nowhere in the proof you use that epsilon is positive, that's probably that you've been cheating somewhere. And this is exactly where we've been cheating. We didn't prove that epsilon was that this delta was positive. And again, I will cheat by just pasting the proof in that case. So what we want to prove that the distance between P1 and P2 is positive. And after simplification, this is equivalent to proving that P1 is not equal to P2. So this is a not symbol, not P first equals P second. So assume that P first is equal to P second. And then I will deduce that epsilon is strictly less than epsilon by a short computation. So this is what proves that delta is positive. And in the end, what was the end of the proof? The end of the proof was to fix x and x prime in x. And then this is why I add typos in my slide. Yeah. So now the goal is indeed what I announced. Let's contrapose and push the negations. So that was this line. And yeah, this is exactly h applied to x prime. And we proved the Hein-Cantor theorem. So of course I went fast using the software. The goal was to show you how it feels and what it looks like with, again, these two parts of the screen, the part where you type commands and ask for help, and the part where you see what remains to be done, what are the assumptions, what are all the objects that happen in the proof. Maybe are there questions about what I just did? Or? This was the demo part of the talk.
Looks good. Very good example.
Yeah, it was
No
impressive.
Now I should switch again to my slides. Yeah. So, okay, so this proof was not so smart in the end because it was just, I mean, it looked okay, but when you realized you should have discussed whether K is empty or not, and in the end you never used that epsilon was positive, and maybe it's not the greatest proof of this theorem. So what is it good for? So the plan of the main slice here is, so you've seen hopefully that it's good when you want to have fun. And it was pretty fun using this software to prove this theorem. And then there are 4 motivations that you can, that looks more serious than having fun. Although, of course, I mean, as usual with research, I mean, having fun is the actual motivation. But I mean, when you're talking to funding agencies or taxpayers, we need to explain that this is good for checking mathematics, explaining mathematics, teaching mathematics, and creating new mathematics. So let's see that. So checking is the obvious reason. It's the one that everybody thinks about when they say formal verification of mathematics. There is this referee's dream that you get a paper to review for a journal, and maybe the paper is 200 pages long, but you don't really care because you only read the introduction, check that the statement is relevant, and that the new ideas are clearly explained, and then all the proof checking is done by the computer. That would be great. And it would be much more efficient, and it would allow introductions to paper that would be much better because people would have time to focus on the introductions and on the ideas. Okay, this dream is not there yet. I mean, it's definitely not there yet. I mean, when I did this demo, it looked like it was fast, but the actual truth, as you can guess, is that explaining mathematics to a computer is extremely time-consuming. And very few mathematicians know how to do that. So if you're already late for a referee report, you shouldn't wait for this core to disappear. So right now, what is more realistic is focus on more specific targets. And there are 2 kinds of targets. There are proofs that are too big to fit in one brain or to be checked by the community. And there are small but very technical fragments of proof. So the first kind of target is things like this. You've got books by Lurie, for instance, about higher topos theory. So this is a 700 pages book with a few applications that are mentioned, but mostly only setting up the scene. Or if you look at people doing holomorphic curves, this is another book, Polyfold and Freedom Theory, 700 pages, no application whatsoever, just only the reference volume for foundations. And there are many examples like this. And nobody can really check everything when you need to read more than 700 pages before getting to any applications. And you don't even need to have controversies or anything. I don't say that people don't believe in this. The example on the right is the current record in my field for a submitted paper that is not yet accepted, despite having no controversy whatsoever. So this is the first, so it looks like a short paper. This is 161 pages, but this is part 1 of this proof. And so the full proof is more like maybe 500 pages. It was submitted in 2012, and it's still under review in a very nice journal that simply cannot find and cannot make the process converge. And yeah, there is no big issue with this proof. It's just extremely long and difficult, and the usual process, which is usually very efficient, and simply doesn't work. Of course, there are also older examples, like nobody really knows whether we know what are finite, what are the simple finite groups or stuff like this that are even bigger proofs. But we are not yet at this point where we can verify huge proofs. But that would be one path forward. I mean, we could decide to focus on proofs that are too long for the community to check. But this is science fiction up to now, the giant proof checking. But what actually already exists is checking a very technical fragment of a giant proof, or not giant proof, but checking fragments. So the best example we have by far is the liquid tensor experiment. So Peter Scholze wrote about 1 year ago, I guess now a bit less than 1 year ago, he wrote a blog post where he explained some theorem, and then he wrote, with this theorem, the hopes that the condensed formalism can be fruitfully applied to real function analysis stands or fall. I think the theorem is of utmost foundational importance. So being 99.9% sure is not enough. And you don't care what it means, condensed mathematics and applying to real function analysis. I mean, this guy is a serious mathematician, and he thinks he proved a very important theorem. This is what you need to remember from this paragraph. And then he continues, as it will be used as a black box, a mistake in this proof could remain uncaught. I spent much of 2019 obsessed with the proof of this theorem, almost getting crazy over it. In the end, we were able to, we is Peter Scholze and Dustin Clausen, able to get an argument pinned down on paper, but I think nobody else has dared to look at the detail of this. And so I still have some small lingering doubts. While I was very happy to see many study groups on condensed mathematics throughout the world, to my knowledge, all of them have stopped short of this proof. Yes, this proof is not much fun. So this proof is, I think, about 30 pages long or something. So it's not at all a giant proof, but it's extremely technical. And there are many things moving in all sorts of directions and with complicated interactions. And it was not clear to Scholze that he really managed to prove that. And it was very clear to him that nobody would check. And indeed, this hasn't changed with the traditional process. But Scholze asked for help. He asked everybody doing formalized mathematics, everybody playing with this software that I showed, or other ones with Coq, with Isabelle, with Mizar, whether we could help him. And then half a year later, he wrote another blog post saying, I'm excited to announce that the experiment, the liquid tensor experiment, has verified the entire part of the argument that I was unsure about. I find it absolutely insane that interactive proof assistants are now at the level that within a very reasonable time span, they can formally verify difficult original research. Congratulations to everyone involved in the formalization. And everyone involved is, and first and most, Johan Comlin, but also a rather large team of other people, Ricardo Brasca, Kevin Buzzard, Heather Macbeth, myself, Bevik Mehta, Scott Morrison, Filippo Nuccio, Damiano Testa, and Adam Topaz. And they are continuing work on this because what was verified was the part of the argument Peter wasn't unsure about, but work continue on this thing. So this is a huge triumph of this idea of checking a carefully chosen, very difficult part, but without checking 1,000 pages of mathematics. So this already exists. Now, there are other reasons to do that. And I think, I mean, the most compelling reason to me is the explaining reason. Because a lot of what we do is explaining mathematics to other people. And this we sort of understand how it works. I mean, nobody can really define what is mathematics, but mathematics communication, this is something which is much easier to talk about and define. And in traditional math writing or talks, the author decides the level of details. I mean, when you write some mathematics, you cannot include explanations about everything. That would be unreadable. So you need to decide what is well known, or maybe what you are too lazy to explain, and then the reader has to adjust. And a very important goal of this formalized mathematics enterprise, at least to my taste, is to let the reader decide on the level of detail. And it doesn't mean that the reader will want to see all details, because again, seeing all the details is completely unbearable. I mean, you can't see all details, but what you want to do is to have a document, probably a web page, where you can start with the very high level overview and just ask to zoom in whatever place you want to visit, and maybe unzoom when you're satisfied with some very specific place that you wanted to check. And right now we don't have a nice interface for doing that, but this is within reach. I mean, so we have this software that gathers all the details. I mean, in the proof that we've seen, there were many details that were not shown at all in my proof. I mean, it went fast, but for instance, I never explained why x times x was compact. I mean, the computer figured out that it was meant to use the fact that the product of compact spaces is compact and stuff like this. And when I was writing d for distance, I was never telling the computer whether I meant the distance in x or the distance in y. The computer just figured out what I meant by inspecting the arguments to the distance functions. And so it's already hiding a lot of information, but it's all there. I mean, you can ask for this information. If I go back quickly, so for instance, here you see I've got distance between x and x prime, and then distance between P1 and P2, and then the distance between f of x and f of x prime. And if I click on this distance, I see that first, this distance is a real number, and this is the distance that I have on y. And if I click on this one, I see this is the distance on x. So it's all there, and many more information is hidden from the interface by default, but you can still get it back. And maybe a very preliminary version of going from heuristic and informal to formal would be to have a look. Does it work if
See it, but I don't hear you. You're muted now, Patrick. There. You're still muted, Patrick. Okay. Are you? I'm not hearing.
It seems that I can't talk and show you a browser at the same time. So let me try something else. Okay, can you see and hear at the same time this time?
Now we can, yes.
Yeah.
Okay, so this is a project I'm currently working on, doing a differential topology and including existence of sphere versions. And you see, this is a text file that was rendered on a web page, but this is a text file rendered using Plastek, text to HTML converter that is written in Python. And you see, I've got definition, and that definition here has a little check mark saying it has been formalized, or this lemma has a little check mark saying that it's been formalized. And if I look at the Lean declaration, the Lean statement that correspond, I can follow a link, and I get on GitHub. I mean, I see the Lean file that is formalizing this statement. But here, now I'm kind of stuck with a web page that is not interactive at all. But the dream is that when things will work, I will be able to go from the text file to the to an interactive version of the Lean code, and without having such a barrier from, I mean, in a much more continuous way. But this is science fiction. But this science fiction that is hopefully not too far away in the future. I mean, the technology is here. It requires engineering and stuff. So now I need to go back to my slides. So the next topic is teaching. So of course, it's you may wonder what's the difference between the previous point and this one. I mean, teaching is not only about explaining mathematics to students. It's also about teaching how to do mathematics to students, and especially teaching how to prove things and teaching how to write proofs. And I've been using Lean, so this software with first-year undergraduates since 2019, so in Orsay, in my university. So they are a double major in computer science and mathematics, pretty good students. And I'm not teaching them any new mathematics. I'm using Lean to train them to reprove stuff that I've already learned in the previous term. So stuff about sequences and functions from real numbers to real numbers. And the goal of the course is to teach them how to write proofs on paper, I mean, pen and paper proofs, but using the proof assistant as an intermediate tool. So I've done that 3 times already. This year will be the 4th one. And in the first 2 years, they were using the software exactly as you saw it, using the same kind of commands that look a bit like programming. And they thought it was easy, actually. It wasn't too bad. The problem is that when they wanted to translate those proofs on paper, then it was difficult. So I switched to changing the input mode a bit so that they would write proofs that would be easier to transfer to traditional proofs. So I will show you what it looks like. I very quickly translated part of my things into English. Yeah. So teaching. So this is something they could see in my lecture. So I define continuous function. So continuous function at a point x0. So a function f is continuous at a point f0 is for all epsilon, etc. And I define that a sequence u tends to a limit L if you've got this definition. And then the thing to prove would be in that case that if you've got a sequence u that tends to x0, then and a function f which is continuous at f0, then it's the sequence f composed u, so the sequence f of un tends to f of x0. So continuity implies sequential continuity. And you see that instead of having the command that I had before, now it looks like kind of English sentences. Let's prove that for all epsilon, and then there's a formula, fix epsilon, which is positive. And this is still interactive Lean. So the main point of using this kind of software with students is not the fact that the software cannot be, that you cannot cheat with the computer. The main point is this static state display. At every step in the proof, the students see what are the objects, the function, the sequence, the point x0, the assumption on u, the assumption on f, epsilon, which is a positive real number, and what is the current goal. And after each line, this state updates. Now I've got a delta, an assumption involving delta, and so on. And at the end of the proof, they get the immediate gratifications that the computer is happy with the proof. So let me insist on the fact that this is not natural language processing. This is extremely rigid syntax. And if you use any variation on those sentences, the computer gets completely confused. And this is not the dream of just taking the source text from archive and formalizing everything by magic. This is completely artificial language. And the students find this is harder to write this than to write the commands that look like programming earlier. But the point is that once they've managed to write this, it's much easier to write a paper proof. And this is the end goal. Okay.
Could you write the commands and translate them to that automatically?
Yeah, we could. Yeah, that could very probably be possible, and there have been work already in this direction. I mean, there would be ambiguity because we tend to have commands doing lots of different things, and then the computer would need to figure out what is the correct sentence to put. So we could make this job easier by having more commands doing more specialized stuff. But yeah, that could be possible. But I want the students to type those things because I mean, otherwise the computer is working a bit too much. I mean, when using these things for teaching, there is always a very delicate balance to find between having the computer being too helpful and not enough helpful. And sometimes the computer is good at doing things by itself that we would want students to do, and sometimes it's not good enough at doing things that it should do alone, and we don't want students to think about some trivial stuff. I mean, it's not easy, but still, I consider this as a successful experiment, but it's not perfect. Let's move on. So what is the next reason to do what we are doing? I don't remember. I need to go back. Oh yeah, the big one. I mean, can you use this to create new mathematics? And because this is meant to be our job as mathematicians. Checking mathematics is not meant to be our primary job, and teaching, it depends a bit. Explaining is a big part of our job, but we need to create new mathematics. So there are many things that you can do using a proof assistance. So first, it's very easy to tweak definition and statements and find unnecessary assumptions, because usually when you write a paper, you've written a definition, and then you write maybe 20 pages using that definition, and you change your mind and you wish you would have used a slightly different definition. But then if you change the definition, you need to check that all the proof still works, or maybe they can be repaired easily, and there is a barrier to tweaking the definition and the statements of the lemma. And with the computer, it's very easy. You can just change the definition and immediately see what is still okay and what is broken, and fix stuff. And we could play the game of adding an unnecessary assumption. Maybe let's do that, even if it's painful to switch from one window to the next one. Let's say in my, what could I add as a stupid assumption? Maybe I think that y should be complete in this theorem. I mean, that sounds good. Maybe I should assume that y is a complete space to get this conclusion. And then, what is it broken here? What? This has broken the proof. No, something bad happened. I probably, okay, I removed the, okay. This has nothing to do with the assumption I was adding. I made a bad move earlier, and I've broken my proof. So now, of course, the proof is still correct. I still get the goals accomplished celebration here, but now I can ask the linter for what it thinks about my file. I mean, it doesn't matter what it means, but here I can see the unused argument linter reports that this argument 5 complete space y is unused. So it's unused, so I should remove it. And you can do much more sophisticated things in this direction. And it happened to me while formalizing stuff in general topology from Bourbaki, that there were unneeded assumptions in Bourbaki, and I completed the proof and thought, I think I didn't use the assumptions, and I just deleted the assumptions, and the Lin was still happy. So indeed, that was unnecessary. Now, the next point is that searching for mathematics should become much easier. This is still science fiction, but you can hope for search engines in formalized mathematics that would be able to find lemmas for you, even if the lemma is not exactly stated the way you've been searching for it. And that will probably require assistance from artificial intelligence. And which brings us to our third point. I mean, artificial intelligence may help. This is still science fiction, but artificial intelligence may be filling easy proofs, or maybe suggesting related statements or analogies using neural network and stuff like that. Many people are working on this, but the results are not yet super impressive. Unless you count, I mean, this suggest command that I used earlier. I mean, if you consider this is artificial intelligence, then it's already useful. But I don't think, I think Scott is around. I mean, the author of this suggest command, I think I've seen him in the participant list. He probably doesn't call it artificial intelligence. And then last but not least, this formalization thing, so explaining mathematics to computer, it encourages clean abstractions. You don't want to have fuzzy ideas and definitions that are not really what you mean when you talk to a computer. And this also brings me to another trick to prove stuff in a proof assistant, is a trick which is directly coming from the real world. The most efficient proof of any theorem is to have someone already proving the theorem. So what happens if I use suggest at the very beginning of the proof? I mean, unsurprisingly, my computer already knows about Heine-Cantor. And so it suggests that I use the fact that this is exactly compact space dot uniform continuous of continuous applied to the assumption HF. And this is the end of the proof. Now I can remove everything else. This is the proof. Okay, so what is this uniform continuous and continuous? I can also jump to the proof. What is it? No. I can click on go to definition to see what is the proof that my computer already knows about. And this is the proof that my computer already knows about. This is this 5-line computation. This is the proof of Heine-Cantor in the library that we are using. So what is this proof? Do you recognize it? So maybe using a PDF version of this proof will be easier. PDF. Let's do PDF. This is this proof. It proves that for any two uniform spaces, x and y, if x is compact and separated, then any continuous function is automatically uniformly continuous. And the proof is this computation. So of course, like my proof, it's using deeper theorem to crush the proof. And the first line is using that x is compact separated to rewrite this u sub x, whatever it is, to inf over x of n of xx. And then there is a small computation. And this is pretty typical from formalized mathematics, that computations are encouraged. You've seen already when I was using suggest all the time in my demo, that explaining mathematics to computer encourages backward chaining in reasoning. So reduction to easier statement, successive reduction, and not forward reasoning, building more and more facts. But it's also favoring this kind of computation proof, but this is not the main point of this slide. The main point is that this is clearly using some abstraction that my proof was not using. And I will very quickly tell you what is this abstraction. So I won't do Heine-Cantor. This is too much. This uniform spaces thing, it would be much too long. I only have 10 minutes remaining. So I will do something very related, but easier. So let's go back to very elementary mathematics. I've got many notions of limits that I teach to my students, limits of a sequence, limit of a function at a point, or maybe limit of a function at a point from the right or from the left. Maybe this is saying that when x goes to x0 from the right, then f of x goes to y0 from the left, or maybe pointed limits, so I remove x0, and the limits could be infinite and stuff like this. So even if you stick to functions from real numbers to real number, the source and target could be plus or minus infinity, a point from the left or from the right, plus variations where the x is not allowed to be equal to x0. And maybe x could be constrained to some dense subset, say rational numbers. So actually, there is not one definition of limit of a function. There is, this is 13 combinations if I did the combinatorics right. So that's 169 definitions, including the behavior at the source and at the target. And now, limits compose. So for instance, if f of x goes to y0 when x goes to x0, and g of x, that should be a y, g of y goes to z0 when y goes to y0, then the composition goes to z0 when x goes to x0. So how many lemmas are we looking at? So there are 13 possibilities for the first slot, 13 possibilities for the intermediate behavior, and 13 possibilities at the endpoint, at the output. So that's actually 2,197 lemmas. Of course, we never prove those 2,000 lemmas. We prove maybe 2 variations, and then we tell students that they can do all the other variations if needed. But this is not good enough for computers. And this was, of course, not good enough for Bourbaki for exactly the same reasons. They wanted to have a clean version of the story. And so they invented filters. And I'm a bit short on time, so I won't really read this slide. But there is a gadget called the filter on a set X. And it's a collection of subsets. And for instance, that could be the collections of all neighborhoods of some point X, or there could be the collections of subset of real numbers containing a half-infinite interval, or maybe collections of natural numbers containing such a array. And all the behaviors, all the 13 behaviors from the previous slides can be encoded into a filter. And then Bourbaki says, given a filter on a set, and on a set X, and a point Y in another set capital Y, you say that the function phi converges to Y along this filter F is for any set in the filter, for any neighborhood of Y, the preimage of this neighborhood belongs to the filter I've been given. So this is in Bourbaki. This was in Bourbaki already in the 1940s. So I don't know, 60 years ago, something like that. But this is not general enough. Strangely enough, they didn't really went far enough with this idea. They were a bit shy with abstraction in Bourbaki. So we need to replace the neighborhood filter by any filter on Y. And then you get a notion of convergence of a function to a filter on Y along any filter on X. And it's not very important what is this definition, but it's very simple. I mean, it's just very simple definition. And now I've got only one definition, whereas previously I had 169 definitions. And I will have only one lemma instead of 2,000 or something lemmas. Because this story of filters, it's extremely structured. If, on a given set X, the filters form a complete lattice. So there is an order relation on filters on X, and you can make the infimum or supremum of any set of filters on X. And there are push forward and pull back operations. You can push forward filters from X to Y, or pull back filters from Y to X if you've got a function from X to Y. And the push forward and pull back, they compose as you think they will. So they push forward is covariant and pull back is contravariant. And more algebraic structure on those things. And the convergence that we were discussing, it simply means that the push forward of the source filter is less than the target filter. This is the one definition to rule the 169 definition we had before. And now I can prove 2000 lemmas, although I only have 3 more minutes. This is the proof of 2000 and whatever lemmas. Now limits compose under this assumption that I've got this limit and this limit, then the composed function tends to h along f just by using the formal properties that are above, especially the push forward composition, which actually is the thing containing that has the mathematical content. The mathematical content of this limit compose thing is this algebraic property. And so the proof of Heine Cantor that we had before was using this technology. Now I can go back to it, just very quickly see that there are indeed push forward. This is a filter on x times x. You can see an infimum of filters and operations and ordered functions and stuff. And of course, I mean, there is mathematical content in this equality. Uniformity on x is infimum on small x of neighborhoods of x comma x. And all the rest is formal. Okay. So I skip that. So what did we gain in this short filter story? This was 100% mathematics, no computer science involved, no software, just smart definition and algebraic structure and generalization. And this doesn't exist in the real world. I mean, first, so Bourbaki didn't went far enough in this direction. This is the first thing. But even what Bourbaki did is not used by real-world mathematicians. And it is everywhere in proof assistance, and not only in Lean. I mean, if you go to Isabelle or Coq, they have filters everywhere. And there is no going back. Once you start thinking in those terms, it's very hard to think about limits and other stuff you can do with filters in the old-fashioned way. So who's playing this game? There are lots of proof assistants. So I mentioned Coq and Isabelle, but there's also Mizar and Whole-Light. And the one I've been using, I said already, was developed mostly by Leonardo Demura, but this is an open source software, and especially the mathematical library that we are using, the one that contains this fancy proof of Heine Cantor, is a very active open source project with about 180 contributors. But this is still a tiny portion of mathematicians, of course. But if you want to join us and have fun with us, you can go to this website, leanprovercommunity.github.io. And what we are doing currently is, so there have been recent stuff, and recent and not so recent. So there are people doing things close to logic and set theory. For instance, independence of the continuum hypothesis from the axioms of Zermelo-Frankel set theory has been formally verified a couple of years ago by J.C. Hahn and Floris van Doorn. And then there have been things in measure theories, so how measure on locally compact groups was done recently, existence and uniqueness. And so also by Floris. And probability was very start to slow in Lean. There have been probability in Isabelle for a long time, but recently Raoul Nicodim, conditional expectation were done, so by Ying and Rémi Dejean respectively. And we are getting to ordinary differential equations with Cauchy-Lipschitz, and we've got a bit of differentiable manifolds. And in algebra, we've done Galois theory. So those are independently, the first 4 names are people working in Coq, who proved the insolvability of the quintic equation. So it is Abel Ruffini. And we had a group in Lean as well, and Browning and Lutz. And people are doing number theory, finiteness of class group of global fields, and doing algebra with fit vectors. And with Kevin Buzzard and Johan Comlin a couple of years ago, we defined perfectoid spaces. So you see, it's going in various directions. Some things are elementary, but we are missing up to recently. Some things are very advanced, like the perfectoid spaces stuff, but really depends on what people are interested in. And currently, we are working on lots of other things. So complex analysis, which is very well developed in Isabelle, is only beginning in Lean. And there are people doing more number theory. Very recently, they started on this Kummer proof of Fermat last theorem for regular primes. I'm doing differential topology with Oliver Nash and Floris van Doorn. And the liquid tensor experiment is still on progress. And very soon there will be a revolution because we will switch to a new version of Lean, Lean 4, which is a complete rewrite that will be much more powerful for us. So this is really the very beginning of this story. So you should feel free to join if you're not already playing this video game. And that's all I wanted to tell you.
Oh, great. Thanks. That's a great talk. Questions? Questions from the audience? I have a question. So the your talk and these proof assistants much emphasize deductive proofs and general statements, and of course mathematicians and physicists such as myself have other forms of reasoning. For example, to have a collection of examples and counterexamples, which to some extent, I guess one can do in these systems, but it's far less convenient. Do you think that that's something that could be improved?
Yeah, we could have many more examples. This is clearly something we are not very good at. And examples and counterexamples, we have some of them. And it's true that it's easier to explain abstract mathematics to a computer than very concrete ones. And it's not only because of taste that we did perfectoid spaces before doing, I don't know what, power series and complex numbers, stuff like that. And it's indeed easier to explain abstract stuff. And of course, people attracted to this game are also attracted to abstract mathematics. And the same reason why Bourbaki is also not so good on examples and concrete stuff. Although they have the exercises, but maybe the examples in the exercises are not so concrete either. No, we are not good, but there are no deep reason why we can't have more examples. We should have more examples, and we will need more counterexamples too. If we want to train neural networks or other kinds of machine learning stuff, they also need to have nice counterexamples to try or learn from, because one of the things that we hope that artificial intelligence will be able to do will be to evaluate whether a given statement is plausible or not, which is of course a big part of a mathematician's activity. The mathematical intuition, the first use is to say, this doesn't look good, or yes, this should be true. And for this, we could use machine learning, even if it's not producing a proof. And clearly, when we do that, I mean, part of what we call our mathematical intuition is built on top of a stock of examples and counterexamples.
Okay, thanks. There's two questions. There's a hand up, but also in the chat, Angeliki, very open-ended, where she says, "Thank you for a great talk." And then the very open-ended question: what will the upcoming changes in Lean 4 be? Maybe.
This is a pretty specialized question, but maybe there are only specialists now. So maybe everybody else flew away. But it's very hard to answer that quickly. But Lean 4 has been rewritten mostly in Lean, so it will be much easier to extend and tweaks, and also it will be faster for heavy weight tactics, and for proof searching and interacting also with automated theorem provers. And so part of the changes will be realizing the goal that was the goal from the very beginning of Lean, to bridge the gap of between automatic theorem proving and interactive theorem proving, having all the good sides in one places. Because so in Lean there is this expressive logic where you can easily express yourself, but then it makes it harder for automation. And in Isabelle, that some people here know very well, the logic is less nice, is less expressive, but it's easier for automated proving. So hopefully in Lean 4 we will have both the expressive logic and the automated proof working together. And yeah.
There's more.
But answering more, I mean, there are many resources if people want to learn what are the promises of Lean 4. But this is a much more specialized question. I want to emphasize that I've used Lean as my example in this talk, but really almost everything I said during this talk applies to any proof assistant, existing or future proof assistants or past.
Okay. Kevin Buzzard.
I'm interested to hear more about your natural language. Why did the students find it difficult?
Because there is a kind of, I don't know how to say that in English, cognitive, I don't know what, fight, because it looks like a natural language, so students are...
Cognitive dissonance or something.
Dissonance. Okay, so actually I should have tried the French word, like we usually do, how French people talking into English. So yeah, so they write whatever comes to their mind, and they are disappointed that the computer doesn't understand. Whereas if it looks like a programming language, because they also have programming classes, they expect the computer to be psycho-rigid.
So could you conceive that you could just write more of those clever little tactics or parsers or whatever they are that could actually make it more likely that their initial guess was correct, or do you think it's just hopeless?
Yeah. I mean, I did that already a bit. There are already variations, but when you add variations and then you want to document things, it also makes things more scary if there are more variations. And also, I mean, those are technical questions, but the more variations you add, the more difficult it becomes to have good error reporting. Because if the parser is trying to understand what you say, and if you make the parser try harder, then it will fail later. And at the point when it fails, if it is very far away from the point where it should have failed, then the error message will be very confusing. And this is a general principle of parsing in software languages. And so, yeah, the more you complicate those things, and the more difficult it gets to have good error messages, which is, of course, crucial. Of course, in my case, it's I've got a huge advantage is when I write my own error messages, I can write them in French. So for my students, it's much easier. But even like this.
Thanks. Peter Gibson.
Hi, yes. My question is sort of related to Kevin's. I was interested in the semi-formal teaching language and whether it is targeting mostly analysis or if it is a generic for...
it's completely generic because the tactics that are exactly the same ones as we saw. I mean, if you thought that what I showed in my long demo, if it's sounded generic enough to you, then the control natural language tactic is exactly as generic as this one is. It's really wrapping those tactics.
And is it available in English at this point, or was it translation?
No, so the French version is on GitHub, and the English version is not complete at all. Basically, I translated enough of my French tactics to be able to give this talk, but and it's a messy. But if there are people interested, it's not difficult to do this translation.
Yeah, I mean,
you need to learn meta programming in Lean. I mean, you need to learn how to write a parser for tactics in Lean, and then how to write easy tactics. but if there is enough interest, I mean, I'm sure we could find someone who has time to do this translation.
Yeah, I guess the general interest here, from my perspective, would be to reduce the distance between what you did at the beginning, where you had a LaTeX file and you imported it into Lean, and then you had to make a few trivial changes. But these trivial changes should be fairly easy to make automatically.
No, but this is a very serious topic. I mean, what I've shown with the control natural language tactic is really a hack for my students, and I'm not a researcher in control natural language stuff, but there are people who think seriously about this.
Sure.
There's of course the group around Köpke in Bonn, I think, but also other people are working on much more robust
Yes.
incarnation of this dream. And I don't know if it will work, but probably someday this. But I mean, at least the control natural language version. I'm not talking about just taking a text file on archive and magically turning it into a proof assistant file. This I find very hard to believe, but you never know. I mean, people playing Go 10 years ago, they were laughing at people playing chess and explaining with a very convincing explanation why computers would never be good at Go and stuff like that. So, of course, we mathematicians think that we are very safe from artificial intelligence and what we are doing could never be done by a computer, but I don't want to risk saying that.
Thank you. That's interesting.
I see there are also activities in the chat. Oh, Suggest versus Sledgehammer. This is completely different. I mean, Suggest is not calling external automated theorem provers, and it's Scott has answered actually, and Scott, who answered the question, wrote Suggest. So probably I shouldn't try to answer.
So there's an interesting chat discussion going on, but if there are more questions, if not, let's thank Patrick again for very interesting talk. And so next week we'll be having Curtis Bright and Vijay Ganesh speaking about solving hard mathematical problems using a combination of SAT solving and computer algebra, I believe. So I look forward to seeing you all next week. Thanks for joining us.
Thanks, Mike.